Okay, everybody, welcome to another week of learning about memorization and generalization in machine learning or AI systems. Today, we're going to talk about an area of machine learning called adversarial machine learning, which is a really cool and exciting area. Why? Well, there's a lot of people out there right now trying to sell you AGI. And I think if you take the time to learn about adversarial machine learning, you can maybe have intelligent questions about like what exactly do we mean by AGI, what do we mean by AI, and really learn more about how deep learning actually works. So this is output that with 3 prompts I got from ChatGPT as a response. You can see it's nonsensical. Maybe some of you can see make some sense of the output and have a good laugh. I was cry laughing when I figured out what was going on. But what I mean is when we learn how to have an adversarial relationship with an AI system, when we learn how to make it give us output that it probably shouldn't give us, we can also learn about how it actually works. And so I come from kind of a hacker mindset, a hacker background. And I think hacking AI systems can teach us a lot about how they work. And I'm not alone. There's many years of research on this. I'm going to show you a YouTube in a YouTube. This is a turtle that was 3D printed. You probably can't see it, but from every angle, this turtle is classified as a rifle. It has this psychedelic looking pattern on it, and this pattern is a specifically chosen noise pattern that takes it from a turtle and it makes it classified as a rifle. And so, how does this exactly happen? Well, maybe you've studied a bit of machine learning. If not, it's no worries. When we do deep learning, we have, again, this iterative process of some type of gradient descent, usually. There's other optimization and loss methods, but usually what, again, we're trying to do, we're trying to go from high error to low error. And when we're doing this, this is a great graphic from a blog that I've linked below. But what we're doing this, we're trying to end up at the minimum loss or error. And when we have these adversarial examples, how do they work? Well, they take an original image and then they add a small amount of, again, carefully chosen adversarial noise. How is it chosen? Well, it's chosen specifically to increase the error. So here we can see we're trying to go down, lower the error. We're now with adversarial noise, we're trying to move in the direction to increase error, increase uncertainty, maybe towards the target class, like rifle, like where we want this panda to be classified as a rifle, or maybe just out of the class that it's currently in. So when you think about this, remember what you learned a little bit about margin theory, and remember that even though we're dealing with nonlinear space, to some degree at each layer, we have some sort of linear space within that layer. And within that, we're basically trying to move out of wherever the region that we're currently in towards the nearest decision boundary or towards a target decision boundary. And with each of these steps, we can kind of move out of this. And these adversarial attacks, they were so cool when they came out because there was no way to defend against them. And every time somebody came up with a defense, it was broken like the next day. So this is a really exciting area of deep learning research because people had to learn more about how deep learning worked to figure out why this is happening and how to address it. And so here again to show the panda, this panda adversarial chosen noise ends up classified as a gibbon, which is not a panda. So initial defenses were really interesting to watch. I was working in the machine learning field and deep learning at the time. And I actually have a CCC talk, I'll link it down here, that you can watch where I presented these types of attacks at a hacker congress. But basically, the initial defenses were perhaps we have some idea of the decision space. And again, maybe in deep learning, we have kind of different views of this at different layers of the network, which is fine. But That decision space has some sort of manifold, which you can think of basically as a nonlinear plane, or you think of it like a blanket on top of something, going through these many hills. And we know that most of what we've seen are near these manifolds or within certain areas of these manifolds, right? Maybe on the inside of a manifold, like inside a sphere. And what adversarial images do, or adversarial examples can also be text or other things, is they activate areas that we don't know about, usually, areas that have not been seen and are therefore kind of classification null spaces to a certain degree. And what early research did is it said, okay, we're going to take these adversarial examples and we're going to repair them. We're going to use maybe autoencoders or other ways to take them from this kind of outside the manifold space and try to fold them in or move them towards the manifold. And that was a lot of really cool, interesting research on how do we build those types of autoencoders that can take something outside of a certain types of decision space and move them or transport them a little bit closer to the decision space that we know. And this might be activating some of your thinking about this memorization, because remember, this memorization works for really common examples. Yeah, that's like the manifold itself, right? Or maybe whatever's in them, those areas. And then it also works for really uncommon examples where we might only have one example, but we know that we're going to be tested on it. And that's a little bit like these adversarial images. So I want you to think about that connection. And another approach was kind of to observe uncertainty, and at certain levels of uncertainty, to either default to this is most likely adversarial and we're not going to respond, or to default to some sort of compression. So to compress the input and try to make another decision because we notice that the network is misbehaving, that the model essentially cannot make an accurate decision. So these were kind of some of the initial defenses. But what actually ended up being the best general defense that came out at the time, so this was a 2018 paper that I'm showing right here called Towards Deep Learning Models Resistant to Adversarial Attacks. And it was as simple as growing the model size and training iterations. Now, when this first happened, I was like, what does this mean about what we're learning? Like, these models are huge compared to other models. They include all of these adversarial examples. This is called adversarial training. And if we're including them, does that mean now that we have new manifolds, we have new decision boundaries that we're learning that also essentially encompass or create new decision space that we can think of as an adversarial decision space? And what does that mean for memorization? Well, I mean, memorization research was kind of just starting around this time. So this was one way of looking at the problem, is maybe we're memorizing some of the adversarial examples as a way to then appropriately classify them when we do inference time. And the reason why we need the growth in model size and iterations is because we need enough space, parameter space, to allow for some semblance of memorization, which again can allow for generalization of other similar examples later. And why do we need the iterations? Well, we need the iterations because we're going to need to see the same examples enough times that we can memorize them, right? So this for me was an aha moment. Before I'm making this video and this blog post, I looked up what's the best defenses now, because I haven't been super active in adversarial learning in a while. And the best defenses now are based on diffusion models. And a really interesting thing. So if you watch some of the earlier videos, you might have learned a few things about a diffusion model, but a diffusion model is really good at reducing noise because that's how it's literally trained. And so in this paper, which is Carlini et al., they add this adversarial noise, and then they use a diffusion model trained with a diffusion process that can remove the noise. And what they found is they only want to run that diffusion process once, because if they run it more than once, it actually starts changing the original input and adding artifacts of the training examples. So you can see here on the left is the original one. The one next to it is the adversarial noise. The one next to that is the one shot. So just run diffusion once. The one next to it is the multi-step diffusion process. And that one, we can see that the diffusion process is like, oh, I don't know what this is. I'll make it into a printer. I know what a printer is. I'm going to turn it into a printer. So yeah, I just have to laugh because it's just this encompasses everything about memorization and machine learning that you need to know if you want to know it. But essentially, since we know diffusion models are really, really good at memorization, this will then eventually, if you do multi-step, it will start turning it into something that it knows from the training data set. So I hope you've had fun learning with me. I want to make sure that this channel is interesting for you and your learning. So take a minute if you've liked the videos thus far to comment and let me know what you like. And then I have a few different types of topics for next. So one will definitely be talking about how do we address memorization? Do we want to address memorization? If so, can we fix it? Then another series that I'm working on is hacking LLMs for fun and for learning about how LLMs work. And then I'm going to definitely do a series this year on internet privacy. So how do internet protocols work? Who can see what information about you when you're using things on the internet or using applications? And are there ways that you can protect your privacy better on the internet? If so, how? And then finally, I'll definitely be doing some stuff on private and personal AI or machine learning systems. If you want to support my work, you can buy my book, or you can also tell people about this channel. So thanks so much. And I look forward to hearing what you want to learn about next, which doesn't have to be any of these. You can also give me new ideas. See you later.